Welcome to the Deep Dive. We dive deep into complex source material so you get the core insights fast.
And today, we're really getting into the nuts and bolts of industrial life across Bangladesh. Our sources give us this incredibly detailed picture. Think of less geography, more operational stress points. We're talking textile mills in Gazapur, power plants out at Meghnad, the whole range.
Exactly. And our job today isn't just to list technical specs. We want to show you, the listener, what makes these places tick economically speaking. It's all about how these, invisible measurements flow. Level, temperature, pressure are actually the visible drivers of success and safety and profit across 8 key sectors.
That's the mission. We've got all this technical data, right? The goal is to pull out the human story, the economic narrative from it. We want to show how every single sensor reading, every time it kicks off some kind of calculation, either financial or safety related. It's more than just engineering. It's the foundation.
Yeah, it really is. And that idea becomes our main theme for this whole deep dive, doesn't it? It's not just about getting the numbers right. It's bigger. It's about integrity, security. You could almost say every sensor tells a story of heat, pressure, flow, and ultimately trust.
Absolutely. Because precise measurement, it isn't just, a technical requirement on a checklist. It's the bedrock. It's how financial deals are verified, how companies prove they meet regulations, and really how the public trusts the products they get, whether that's electricity, the clothes they wear, or even clean water. It underpins so much across the country.
Okay, let's jump in and maybe start where the stakes feel, highest, the power and independent power producer sector, the IPPs. It's really not an overstatement to say every drop of fuel here is money.
Oh, scale is just huge. You're looking at over 25,000 megawatts of generation capacity in Bangladesh. And it comes from a real mix. Combined cycle gas turbines, CCGTs, heavy fuel oil, HFO, high-speed diesel, HSD, coal, even some renewables starting to come in. The big players, Summit, United Power, L&T, they live and die by optimization. Even a tiny inaccuracy, like a fraction of a percent, means massive financial swings.
And the pain points, they're not subtle, are they? The sources talk about unplanned shutdowns, of course, but also this constant bleed, millions lost because the fuel metering isn't spot on. The utility gets billed for gas or oil they can't actually confirm they received. And then there's the big one, the safety risk tied directly to instruments. Boiler level failure. It sounds terrifying.
It really is. And this sector is a perfect example of how instrumentation shifts from just being about efficiency to being absolutely critical for safety.
Okay, let's break that down then. Fuel handling first. Whether it's gas or oil coming in, what tech gives them that financial certainty? The custody transfer piece.
Right, custody transfer, that specific point where ownership in the bill changes hands. Needs top-tier precision. So we're talking things like ultrasonic gas flow meters and Coriolis flow meters. For natural gas, ultrasonic meters are key. They use sound pulses, right, to measure the flow. But gas is tricky. It's compressible.
Meaning its volume changes with pressure and temperature.
Exactly. Which makes billing tricky if you just measure volume.
So wait, if the volume isn't fixed, how can they possibly guarantee the billing is fair?
That's the million-dollar question, literally sometimes. The real product being sold isn't volume, it's energy, measured in BTUs. So the ultrasonic meter gives you that super accurate real-time volume, but also the pressure and temperature data. That feeds into a flow computer, but it needs one more piece of information.
Which comes from the gas chromatograph. That's the thing that checks the gas quality, isn't it?
Precisely. The GC analyzes the actual makeup of the gas, how much methane, ethane, propane, all that stuff. From that, it calculates the exact energy content, the BTU value per cubic foot. You combine the accurate volume from the ultrasonic meter with the energy content for the GC.
And then you know exactly how much energy you've received.
Exactly. Yeah. And certainly if you're buying, say, $1 billion of gas a year, that 0.1% error, which sounds tiny, isn't tiny anymore. It's $1 million potential dispute. High accuracy custody metering, it just eliminates that argument, builds trust.
Makes sense. Now, beyond gas, lots of these IPPs use heavy fuel oil, HFO, and the sources flagged a specific challenge there managing viscosity.
Yeah, HFO is thick stuff, almost like tar at room temperature. You have to heat it precisely to get the right viscosity, thick cream so it flows properly and burns efficiently in the engines or boilers. Too thick, it strains the pumps, might cause them to fail. Too thin, and the injectors can get fouled or damaged. It's a delicate balance.
So what keeps it in that sweet spot?
That's where viscosity analyzers come in, along with really accurate temperature transmitters. They constantly monitor the HFO as it circulates through the heating loop, making sure it stays at that perfect temperature and viscosity. Prevents fuel starvation, keeps the engines running smoothly, avoids costly shutdowns.
Okay, let's switch to that critical safety issue you raised, the boiler drum drama.
Yeah.
You said if the water level drops too low, it's not just a shutdown, it's a potential catastrophe.
It's the nightmare scenario, a dry fire explosion. If the boiler tubes, which are incredibly hot, lose their water cooling, they overheat almost instantly. They can rupture, potentially breaching the entire pressure vessel. It's incredibly dangerous. So the water level measurement system, it has to be absolutely fail-safe.
Right, what kind of technology can even survive in there? We're talking immense pressure, high temperatures, lots of turbulence, right?
Yeah, it's a brutal environment. The go-to solution now is high-temperature guided wave radar, GWR. Older tech, like differential pressure transmitters, can get fooled by density changes in the water and steam mix or by the sheer turbulence. GWR works differently. It sends a low-energy microwave pulse down a solid metal probe.
Okay.
The surface of the water creates a change in impedance, basically a reflection, and the radar measures the time it takes for that pulse to travel down and back up. Because the wave is physically guided by the probe, it stays accurate even with all the steam, foam, and boiling happening inside.
And you emphasize dual redundancy. That's mandatory.
Absolutely non-negotiable, because failure is just not an option. You always install two completely independent GWR systems. If one sensor has an issue or its probe gets damaged, the control system instantly switches to the secondary sensor. It ensures continuous, verifiable monitoring. The cost of that second sensor is nothing compared to the cost of a single dry fire incident.
Makes total sense. And that focus on keeping things running well, the efficiency part, it goes beyond just fuel, right? How does instrumentation protect the boiler itself?
By watching the water quality, specifically using conductivity sensors. If the water used to generate steam isn't pure enough, if it has too many dissolved minerals, those minerals bake onto the hot boiler tubes. That's called scaling.
Like lime scale in a kettle, but on a massive industrial scale.
Exactly. And that scale acts like insulation. It dramatically cuts down how effectively heat transfers from the fire to the water, wasting huge amounts of fuel. It can also cause hotspots that damage the tubes. So monitoring conductivity ensures only ultra-pure water is fed to the boiler, maximizing heat transfer, saving fuel, and making the boiler last longer.
We saw a great example of this ROI in the sources, the Magnacot CCGT plant upgrade.
Oh, that case study is fantastic. It shows both sides perfectly. On the revenue side, they swapped out older gas meters for certified custody transfer ultrasonic ones. Result: an immediate, documented 0.7% improvement in billing accuracy. Seems small, but for them, it meant millions in verified revenue they were previously losing.
Wow.
Then on the efficiency side, they looked at their cooling towers. They installed dissolved oxygen, or DO control. By optimizing the oxygen level in the cooling water, they reduced both scaling and corrosion in the system. This allowed them to slow down the massive the blowers, cutting the energy they use by 12%. It's the whole package. Securing revenue, maximizing efficiency.
It really hammers home that strategic control point, which leads perfectly to that slogan the power sector seems to live by. Fuel measurement equals revenue. Boiler level equals safety. Cooling control equals efficiency. Reliability pays for itself.
All right, let's pivot now to the other giant in the energy space, oil and gas, including the refineries. This feels like a journey upstream, midstream, downstream. And again, safety, accuracy, trust are the watchwords. Yeah, you're tracking the hydrocarbon all the way from the ground to the finished product. Upstream, you've got extraction, like with Baypex at the wells. Midstream is the transport, the pipelines, think GTCL. And downstream is the processing, the refineries, like Eastern Refinery. And yeah, at every single stage, how well you measure determines whether you're making or losing millions.
Okay, let's start upstream then, at the source. The wellhead. You called the instruments there the guardians of the wellhead. What exactly are they guarding against, and with what tech?
They're guarding against, well, chaos, basically. High pressure, volatile fluid. So you have pressure transmitters right there, monitoring the well output constantly, essential for managing flow, preventing blowouts. You'll often find Coriolis meters there too, tracking condensate, the liquid hydrocarbons coming up with the gas. They measure mass flow and density, giving really early crucial data on what the well is actually producing.
And the sources mentioned something really interesting, acoustic monitors. Listening for sand. Why listen for sand?
It's like preventative medicine using sound. Sand production means tiny particles of rock are breaking loose downhole and flowing up with the oil or gas. It tells you the well formation might be getting unstable. But the immediate danger is erosion. Those abrasive sand particles, moving at high speed, act like sandblasters on the inside of pipes, valves, especially choke valves.
Ouch.
Yeah, they can wear through critical equipment incredibly fast, leading to leaks, failures, potentially catastrophic blowouts. These acoustic monitors are tuned to detect the specific high-frequency sound signature sand makes as it hits the pipe walls. They hear it long before you see any damage, allowing operators to adjust flow rates or pressures to manage the sand production and protect the equipment. It's all about preserving the well's integrity.
That's incredibly clever, protecting the asset literally by listening to it. Okay, moving midstream now. The pipelines, like GTCL manages, here we hit that custody transfer challenge. Again, high stakes for billing.
Absolutely. This is the main artery for gas transport. Custody transfer here demands extreme accuracy, often 0.1% or even better. Again, high-accuracy ultrasonic meters are the workhorses, specifically calibrated and certified to meet stringent international custody transfer standards. When you're moving billions of cubic feet of gas, that tiny percentage point accuracy is the only thing that guarantees fair billing and prevents disputes.
And like before, volume alone isn't the whole story. You need the energy content.
Correct. Gas chromatographs are vital here too, constantly sampling and analyzing the gas composition. If the BTU content drops, even slightly, the buyer needs to know immediately because they're paying for energy, not just volume. Having that verifiable data trail from both the flow meter and the GC is what keeps the commercial side smooth. It stops arguments before they start.
Given we're talking about flammable, sometimes toxic hydrocarbons, the safety imperative must be huge across all these stages.
It absolutely defines instrument selection. Everything has to be certified for hazardous areas, usually ATEX or I6 standards. That means the instrument is designed to be intrinsically safe or housed in an explosion-proof enclosure, ensuring it absolutely cannot create a spark that could ignite the surrounding atmosphere. That's non-negotiable. But beyond explosions, there's the silent threat: corrosion.
What's the main culprit for corrosion in oil and gas?
Often it's hydrogen sulfide, HEO sour gas. It's highly toxic to people, and it's incredibly aggressive towards standard materials like carbon steel or even basic stainless steel. So instruments that come into contact with sour gas, their wetted parts, have to be made from really specialized exotic materials. Think super duplex stainless steel, Monel, Hastelloy sometimes.
Sounds expensive.
It is, but the cost of the material is insignificant compared to the cost of a failure, a leak, an explosion, environmental damage, loss of life. Choosing the right material isn't about saving money on the sensor, it's about ensuring long-term, safe, reliable operation in a really hostile environment.
Okay, and then downstream, at the refinery, you've got these massive storage tanks. How do they prevent dangerous overfills?
This is heavily regulated. It usually requires what's called Safety Integrity Level 2, or SESILE 2, overfill protection. SESILE is a formal engineering standard for safety systems. SESILE 2 means the system has a very high, mathematically proven probability of working when needed. For tank overfill, they often use radar-level transmitters. These are non-contact sensors. They bounce microwaves off the liquid surface. The SESILE 2 rating applies not just to the sensor, but the whole safety loop sensor, logic solver, final control element like a valve. It provides an independent safety layer that will shut things down if the primary control system fails, preventing a major spill.
That level of engineered safety makes sense, and the DTCL success story you mentioned really highlights the cost of not having accurate measurement.
Yeah, it's a classic case. They were using older differential pressure orifice plates. DP plates are cheap initially, but they wear out, the orifice edge gets damaged, they're sensitive to pressure changes, accuracy drifts, maintenance is high. This led to constant discrepancies in their billing, unaccounted for gas. By upgrading a key custody station to modern certified Coriolis and ultrasonic meters, they saw their unaccounted gas losses drop by 3% to 5%.
That's a huge recovery.
Massive, immediate financial gain. But just as importantly, it ended the endless, time-consuming billing disputes with their customers. The accurate data created transparency and trust.
It really drives home that core principle again. Accurate measurement is revenue protection. Every SCFM of gas is money.
Okay, let's shift gears. We're moving from energy, that invisible flow, to the industries that literally build the physical foundation of the country.
Cement and steel.
Starting with cement, this is just enormous scale, isn't it? Over 42 million tons produced annually in Bangladesh, and the heart of it all is that rotary kiln. The sources called it the Dragon, burning incredibly hot, like 1400 degrees Celsius inside. That kiln is the heart, and keeping it stable, keeping that dragon happy, is everything. The pain points are constant battles. First, astronomical fuel costs. You're feeding a massive fire 247. Second, quality problems. If flow meters measuring raw materials clog up with dust, the mix is wrong, the final cement quality suffers. And third, environmental compliance. If they exceed dust emission limits, they face heavy fines from the DOE.
So the instruments basically have to tame that fire, yeah. Ensure steady heat, manage all that dust. How do they get precise control over the fuel and air going in?
Okay, let's start with the fuel. It's often pulverized coal, blown in with air. For this, thermal mass flow meters, TMFs, are really key. Unlike meters that measure volume, TMFs work by measuring heat loss from a heated sensor as the coal dust and air mixture flows past it. This gives a direct measurement of mass flow, which is exactly what you need for the chemical reaction of combustion.
And why is getting that fuel to air ratio just right so important? It's not just about saving fuel, is it?
No, it's much more than that. The right ratio gives you stable, consistent heat inside the kiln's burning zone. If the temperature swings wildly, the refractory lining the expensive, specialized bricks lining the inside of the kiln suffers thermal shock. It cracks, degrades much faster. So, precise control saves fuel, yes, but it also dramatically extends the life of that million-dollar refractory lining. Means less downtime, lower maintenance costs. TMFs are also used to optimize the airflow in the pneumatic conveyors that move the raw meal and cement dust around, cutting down the electricity used by those big blowers.
Okay, and monitoring the inferno itself, that 1400-degree burning zone, what tech can handle that and keep the temperature rock steady?
You need really specialized, tough, high-temperature sensors. We're talking high-temperature thermocouples, which physically sit in protected wells near the heat, and infrared pyrometers. Pyrometers are cool. They're non-contact. They sit outside the kiln looking through a viewport and measure the infrared radiation coming off the red-hot clinker material itself.
So they read the temperature from a distance.
Exactly. Gives you an immediate, accurate surface temperature reading. You combine that data with, say, Coriolis meters precisely measuring the fuel flow to the burners, and you get incredibly tight control over the heat profile. That's what ensures you make high-quality clinker consistently. Oh, and pressure transmitters are also vital, monitoring the draft inside the kiln, making sure gases flow correctly, and preventing dangerous pressure buildups or backflow. That's a major safety issue.
Right. And the other big headache, compliance. Specifically, dust coming out of the stacks, usually after passing through huge filter systems called baghouses.
Yeah, and this is where good measurement is both about compliance and operational savings. You have online dust analyzers mounted right in the stack, continuously monitoring the amount of particulate matter going out into the atmosphere. At the same time, you use differential pressure transmitters, DPTs, across the filter bags inside the baghouse.
Why measure the pressure difference across the filters?
Because as dust builds up on the filter bags, it gets harder for air to pass through. The pressure drop, the difference in pressure before and after the bags, increases. Monitoring that DPT reading tells you exactly when the filters are starting to get clogged.
Ah, so it triggers cleaning.
Precisely. When the pressure drop hits a set point, it automatically triggers a cleaning cycle, usually jets of compressed air pulsing the bags to shake the dust off. This keeps the filters working efficiently, prevents them from getting blinded or damaged, extends the life of those expensive filter bags, and guarantees the plant stays within the DOE emission limits. No fines, no forced shutdowns.
So it's total control, really. Stable fire, less fuel, longer kiln life, and staying compliant.
It's the whole package, ensuring quality product and continuous efficient operation.
Makes sense. And that memorable one-liner for cement feels spot on. Your kiln breathes through our instruments. Okay, let's jump over to steel. Another world of intense heat. Electric arc furnaces, EAFs, hitting 1600 degrees Celsius. This is where strength is literally forged, and it demands incredible control over heat. Bangladesh is making around 8.5 million tons a year now.
Yeah, and the pain points here are, well, brutal. Temperature instability isn't just inefficient, it leads directly to rejected products. Billets cracking, steel not meeting the required metallurgical properties, huge waste. And energy loss is massive too, often tied to problems with the cooling water systems. If you can't manage the heat precisely, you simply can't make good steel reliably.
So how do instruments protect the furnace itself, keep it from melting down, basically?
The furnace shell, especially around the EAF, is water-cooled using complex jacketed panels. So you have RTDs and thermocouples monitoring the refractory wall temperature right up close to the molten steel. But crucially, you use electromagnetic flow meters, EMFs, to constantly measure the flow rate of that cooling water circulating through the panels.
Why EMFs specifically for that cooling water?
EMFs are great for water-based liquids, even if they're not perfectly clean, because they have no moving parts to clog or wear out, and they're very accurate. That cooling water flow is absolutely critical. If it drops, even for a second, the furnace panels can overheat and fail catastrophically. So the EMF reading isn't just for efficiency, it's a primary safety function protecting the furnace structure.
Got it. Okay, moving downstream a bit, reheating the steel before it gets rolled into beams or rods, how do they control that efficiently?
Right. Billets or slabs need to be reheated uniformly before rolling. This is usually done in gas-fired reheating furnaces. Here, Coriolis flow meters are often used to measure the natural gas fuel flow.
Mhm.
Because Coriolis measures mass directly, it gives perfect control over the energy input, the BTUs, going into the furnace, regardless of gas pressure or temperature changes. The sources indicated this typically saves 4% to 7% in fuel compared to just using volumetric meters.
And what about that critical cooling step right after casting? You mentioned cracking is a big risk there.
Yes, in the continuous casting machine, or CCM. As the molten steel solidifies into a billet or slab, it's cooled with carefully controlled water sprays. Too much water, too fast, and the steel cools unevenly, causing internal stresses and cracks. Too slow, and the process is inefficient. EMFs are used again here to precisely control the flow rate to each spray nozzle zone. Getting that cooling profile exactly right is key to preventing defects.
And then, right at the end, before the steel ships out, is there a final quality check using temperature?
Absolutely. Temperature sensors, often non-contact pyrometers again, are positioned right at the exit of the final rolling mill stand. This measurement confirms that the steel has finished the rolling process at the precise temperature required to achieve the desired final grain structure and mechanical properties, its strength, ductility, etc. It's the final stamp of quality assurance.
And like cement, steel has a significant environmental footprint, especially with water.
Definitely. Steelmaking uses a lot of water. And like cement plants, they have dust analyzers and DPTs monitoring stack emissions from furnaces and material handling. But the water side is huge. Their effluent treatment plant, the ETP, uses sensors like pH and turbidity to monitor water quality before discharge. But importantly, good monitoring allows them to implement sophisticated water recycling systems. Our sources suggest well-run plants can recycle and reuse up to 40% of their processed wastewater. That's a massive saving on freshwater intake and discharge treatment costs.
It really shows how intertwined efficiency, quality, and environment are, which makes the final slogan for steel very fitting. Every stable temperature means stronger steel and stronger profit.
Right, let's move into industries that touch the consumer more directly, where precision isn't just about structural integrity, it's about controlling things like color, taste, hygiene. Brand reputation hangs on this.
And we have to start with textile and dyeing. I mean, Bangladesh is the world's second biggest exporter of ready-made garments. The whole industry hinges on getting water, steam, and chemistry exactly right.
And the sources painted a really clear picture of the daily struggles, the factory rhythm being constantly disrupted. They talked about three main things. First, shade variation. Getting the color wrong means entire batches get rejected. Huge financial hit. Second, spiraling steam costs. Steam is used everywhere for heating, and it eats into already tight margins. Third, ETP noncompliance. Failing to treat wastewater properly risks losing crucial international certifications like GOTS or ZLD, Zero Liquid Discharge. That's almost an existential threat for exporters.
Okay, let's unpack the money side first, the steam cost.
Yeah.
If steam is the main energy source for heating dye baths and drying, how do they control that cost?
Utility efficiency becomes critical. Vortex flow meters are a key technology here. They work by putting a small obstruction, called a shutter bar, into the steam pipe. As steam flows past it, it creates little swirls, vortices on alternating sides. The meter counts the frequency of these vortices, which is directly proportional to the flow rate. They're robust, handle the typical steam pressures, well, maybe 3 to 18 bar. And getting an accurate steam measurement does two crucial things. One, it tells you exactly how much energy each dyeing machine or process is using so you can optimize recipes. Two, and maybe more importantly, it quickly reveals leaks. Faulty steam traps, leaking pipe joints. They waste enormous amounts of steam.
And you found a specific example of the savings.
Yes. One mill reported cutting their monthly fuel bill by 6% almost immediately after installing Vortex meters on their main steam lines. The data just pointed straight to where the losses were happening. They fixed the leaks and boom, instant savings. For a textile mill, 6% is huge.
Wow, okay. Now for the really tricky part, the color. Shade control. Getting that perfect, consistent color batch after batch must be incredibly difficult.
It is the absolute highest priority for quality. Precision is everything. For the dyes themselves, especially the thick, viscous liquid ones, Coriolis mass flow meters are often the choice.
Right.
Because they measure mass directly, not volume, they aren't fooled by changes in dye density or temperature. You get the exact weight of dye dosed every time, But the chemical reaction that actually fixes the dye onto the fabric, that's incredibly sensitive to temperature.
Right, and that's where the high-accuracy temperature sensors are critical.
Exactly. PT100 RTD's resistance temperature detectors are standard for this. They offer very high accuracy and stability. The sources highlighted how just a 5 degrees Celsius deviation in the dye bath temperature can completely mess up the chemical reaction, change the shade, and lead to the whole batch being rejected. You need that tight sub-degree control the PT100 provides.
And it's not just temperature, right? The chemistry of the bath matters for fixing the color, too.
Absolutely. You need the right pH, the acidity or alkalinity for the dye molecules to properly bond with the fibers. Digital sensors, particularly Memosun's technology for pH and conductivity, are increasingly used here. They monitor the bath conditions constantly. If the pH drifts, the color uptake changes, the shade varies. These sensors help ensure that the chemical environment is perfect for consistent, repeatable dyeing. Gets rid of a lot of the guesswork and rework.
Okay, and then finally, the ETP compliance check. You said this is make or break for exporters.
It really is. Big international brands are under huge pressure to ensure their supply chains are sustainable. Textile wastewater is notoriously difficult to treat. Lots of dyes, chemicals, salts. The ETP has to bring that water back within strict legal limits before discharge, typically pH between 6.5 and 8.5, low BOD, COD, TSS, sensors for pH, dissolved oxygen, DO for the biological treatment stage, and ORP, oxidation reduction potential for certain chemical treatments, are essential to automate and control this process. If those sensors fail or the readings drift, the plant risks discharging non-compliant water, which can lead to fines, shutdowns, and losing those vital certifications needed to sell to major retailers.
And given all those chemicals, the instruments themselves must take a beating.
Oh, definitely. It's a corrosive environment. Choosing the right materials is crucial for sensor survival. You'll see wetted parts made from Hastel AC or robust 316L stainless steel to resist chlorides. For pH measurement in the ETP, non-glass sensors are often preferred for safety and durability. And sensor designs with flat, smooth diaphragms help prevent the thick dye solutions from coating the sensor face and causing inaccurate readings. Material choice is key to long-term reliability.
It all comes back to control, doesn't it? Which makes that textile one-liner very appropriate. Control steam, control cost. All right, let's move to our second consumer-focused sector, food and beverage, F&B. This is growing fast in Bangladesh, and it seems obsessed with two things: hygiene and consistency, driven by standards like HACCP and ISO 22000.
Absolutely. And the pain points here hit the consumer directly. An off-taste in their favorite juice. Waste because expensive ingredients like syrups are overfilled. Or worst of all, a contamination scare. Any of these can kill brand loyalty instantly. So precision here isn't just about efficiency. It's about safeguarding consumer trust in every single bottle, package, or can.
Okay, let's look at the guardians of hygiene and quality in F&B. Where does safety start?
Temperature's number one. Pasteurization, sterilization. These processes rely on hitting and holding exact temperatures for specific times to kill harmful bacteria like Salmonella or Listeria. High-accuracy PT100 RTDs are critical here. They ensure the product is safe without damaging its taste, texture, or nutritional value.
Yeah.
Get the temperature wrong, and you either have unsafe product or cooked-tasting product. Neither is good.
Right. But ensuring safety is one thing. Ensuring people come back for the taste, that's about consistency. How's that managed?
Dosing accuracy is key, especially for valuable ingredients. Syrups and soft drinks, flavor concentrates, fruit purees. Coriolis mass flow meters are the gold standard. Why? Because they measure mass directly. So if the syrup density changes slightly because the temperature fluctuates, a Coriolis meter still delivers the exact weight needed for the recipe. Volumetric meters would get that wrong. This guarantees the taste profile is identical, batch after batch after batch.
And that precision saves money too, right? You mentioned the Narsinda juice example.
Exactly. That juice manufacturer installed Coriolis meters for their syrup dosing. The result? A 12% to 15% reduction in syrup overuse. Syrup is expensive. That's pure profit straight back to the bottom line. They also saw a 9% to 13% drop in steam costs by improving their heating controls. And crucially, customer complaints about taste variation. Eliminated. It paid for itself very quickly.
Okay, let's talk about the cleaning process. The sources called it the clean heartbeat, the clean in place, or CIP system.
Yeah, CIP is fundamental to hygiene. It's the automated system that washes and sterilizes all the pipes, tanks, and fillers between production runs, usually using cycles of hot water, caustic soda, acid, and final rinse. The challenge is getting the chemical concentrations right. Too weak, and you don't achieve proper sterilization, a huge contamination risk. Too strong, and you're wasting expensive chemicals, water, energy, and potentially corroding your equipment over time.
So how do sensors make CIP smart?
By using conductivity and pH sensors right in the CIP return lines. Conductivity sensors measure the ionic strength of the solution, which tells you the concentration of the caustic or acid. pH confirms the neutralization during rinsing. Instead of just running cleaning cycles for a fixed, often excessive amount of time, the system monitors these sensors. It knows exactly when the detergent concentration is correct, and it knows exactly when the final rinse water is clean. Low conductivity, neutral pH.
And the savings from automating that.
They can be really significant. Smart CIP systems often cut chemical and water consumption by 20% to 30%. The system uses only what's needed, confirms the clean, then stops. Faster changeovers, less waste, more confidence in the cleaning effectiveness.
And finally, there's a strict hygiene code for the instruments themselves in F&B, isn't there?
Absolutely. It's all driven by regulations like FDA rules or standards like USP Class 6 for materials. Instruments must be designed for cleanability. That means materials like 316L stainless steel, usually polished to a very smooth finish, low Ray value, so bacteria can't stick. Connections are typically sanitary tri-clamps, not threaded fittings to eliminate crevices, and the overall system design avoids dead leg sections of pipe where product could stagnate. The sensors themselves also need to be tough enough to withstand the high temperatures of steam sterilization, SIP, and the harsh CIP chemicals without failing or leaching anything into the product.
It's clear that precision permeates everything, which brings us to that simple but powerful mandate for F&B. Taste needs measurement.
Okay, shifting again now into highly specialized manufacturing. The drivers here are quite distinct. For pharma, it's all about absolute purity, traceability, and compliance. For chemicals and fertilizers, it's about surviving extreme conditions, sheer endurance.
Let's start with pharmaceuticals. Here, purity and precision aren't just goals, they're non-negotiable. Failing to comply with GMP good manufacturing practices or FDA regulations, that can literally shut a company down.
Yeah, the stakes are incredibly high.
Mm-hmm.
And the pain points are often less about visible breakdowns and more insidious. Things like tiny errors creeping in through manual data recording, breaking the chain of traceability, the constant risk of microscopic cross-contamination between different drug batches, and just the sheer time, effort, and paperwork involved in validating every single measurement point to satisfy regulators. What the pharma industry needs is instrumentation that delivers not just accuracy, but an absolutely bulletproof audit trail.
So if efficiency is already pretty high in pharma, what's the real value proposition of advanced instrumentation? It's not just about shaving off a few seconds here or there.
Exactly. The ultimate value is compliance assurance and brand protection. It's about confidence. And this is where digital sensor technology, especially something like MemoSens, really shines.
Okay, we need to unpack MemoSens. What makes that digital signal fundamentally better than a traditional analog one in this specific environment?
Think about old tech versus new. An old analog sensor sends a tiny electrical signal, maybe 4 to 20 milliamps, down a long cable to the control system. That signal is vulnerable. Moisture getting into the connector, electrical noise from nearby motors, corrosion on the terminals, any of these can slightly change the signal, causing measurement drift. You might not even notice it until your next calibration check, but the data in between could be compromised.
Right. Big problem for traceability.
Huge. MemoSens changes the game. The sensor itself has digital processing built in. It converts the measurement to a digital signal right there in the sensor head. Then it stores its own calibration data digitally inside the sensor. And the connection to the cable, it's inductive, contactless, like charging your phone wirelessly.
No metal pins to corrode.
Exactly. No physical contact means no issues with moisture, corrosion, or bad connections interfering with the signal transmission. The measurement data travels digitally, immune to electrical noise. This gives you incredible reliability, and the traceability is built in.
How does that simplify validation for, say, the FDA?
Dramatically. A technician can take a sensor, calibrated offline in the clean, controlled environment of the lab, and store that calibration data right in the sensor head. Then they walk out to the process line, quickly swap the old sensor for the newly calibrated one. The inductive connection means it's literally plug and play, no wiring fuss. The system instantly recognizes the new sensor and its calibration data. The entire history, who calibrated it, when, what the results were, is stored digitally. It makes audits so much easier and eliminates the risk of using a poorly calibrated or mismatched sensor.
So like you said, they're not just buying a better pH sensor, they're buying an easier audit, less risk.
They're buying confidence, peace of mind. They're buying the verifiable proof that their critical measurements are accurate and traceable, which is arguably their most valuable asset when facing regulators.
It really underscores that core message for pharma. Automation is not just for efficiency, it's for compliance and peace of mind.
Mm.
Okay, now let's swing to the complete opposite end of the spectrum, the chemical and fertilizer sector. If pharma is about pristine clean rooms, this is about, well, surviving chemical warfare, basically. Acids, alkalis, aggressive solvents, corrosive vapors.
Yeah, if pharma is about purity, this sector is defined by punishment. Instruments don't just drift here, they get actively attacked and destroyed by the process chemicals. The pain points are relentless. Frequent equipment failure because the materials just can't hold up, readings that wander off because the sensor diaphragm is being eaten away,
Yeah.
and genuinely unsafe conditions developing because an incompatible material choice led to a leak or rupture.
So survival is the #1 priority for instrumentation here. It's got to be the defense line against the corrosive onslaught.
Absolutely. Forget fancy features for a minute. The discussion starts and ends with material science. You put standard 316 stainless steel in contact with hot, concentrated sulfuric acid or wet chlorine gas. It might last weeks, maybe only days. So you have to choose instruments specifically designed with materials that can withstand that specific chemical environment.
What kind of material solutions are we talking about?
It depends on the chemical, but you see things like flow meters lined with PTFE Teflon because it's incredibly inert, resistant to almost everything.
Yeah.
For pressure sensors, instead of a thin metal diaphragm, you might use a thick, robust ceramic diaphragm, which handles abrasion and resists a wide range of chemicals extremely well. For measuring the level in a tank of fuming acid, non-contact radar-level transmitters are ideal. The radar sensor itself sits safely above the liquid, measuring the level without ever touching the corrosive fluid.
It's fascinating how the housing, the lining, the diaphragm material, the physical construction becomes the most critical spec.
It absolutely is. It dictates whether that instrument will provide reliable data for years or whether it will fail prematurely, requiring costly replacement, causing process upsets, and potentially creating a serious safety hazard from leaks. Choosing the right material, maybe it's titanium for certain chlorides, maybe tantalum for hot acids, maybe specific plastics like PFA or PVDF, that's the fundamental engineering decision for instrumentation in this sector.
A hard-won lesson, I'm sure, which leads to that very practical mantra. Use the right material, and your plant will talk to you for years.
Okay, so we've seen how individual factories like textiles or chemicals manage their own wastewater in their effluent treatment plants, their ETPs. But now we need to zoom out a bit and look at the bigger picture, the national push for sustainability in Bangladesh. Managing water and wastewater isn't just good practice anymore. It's becoming a core survival strategy.
And the compliance pressure is intense, right? For any major industry, having a properly functioning, certified ETP or STP, sewage treatment plant, isn't optional. It's basically their license to operate. The Department of Environment, the DOE, sets really strict limits on what can be discharged.
Very strict. The pH of discharged water usually has to be neutral, say between 6.5 and 8.5. And there are tight limits on things like BOD, biological oxygen demand, COD, chemical oxygen demand, and TSS, total suspended solids. But the real game changer, the thing putting immense pressure on industries now, is the mandate for OSIM's online continuous monitoring systems.
Right, this is the 247 Big Brother aspect, isn't it? These systems aren't just recording data for the plant's internal logs, they are directly linked online to the DOE's central servers.
Exactly. The instrument becomes the official legal witness to the plant's environmental performance. If the discharge water goes out of spec, maybe the pH spikes or solids go up even for a short time, the DOE knows about it almost instantly. That can trigger immediate inspections, fines, even orders to halt operation. This constant scrutiny demands incredibly reliable sensors for pH, TSS, flow, sometimes CRD or ammonia that can operate continuously, often with self-cleaning mechanisms, because that data integrity has to be maintained around the clock. There's no hiding anymore.
But that compliance pressure, it also creates opportunities, doesn't it? Opportunities to save money through smarter water management, the smart fixes the sources mentioned?
Yes, absolutely. When you're forced to measure accurately and continuously, you suddenly have the data to optimize. Chemical dosing is a huge one. Traditionally, operators might have just dumped in extra acid or caustic for pH neutralization, just to be safe. Now, you can link the dosing pumps directly to the online pH or conductivity sensor readings. The system doses exactly the amount of chemical needed, no more, no less.
And the saving.
Often significant. Precise, automated dosing control can cut chemical consumption by up to 18%. That's a big operational cost saving.
And what about energy use? I imagine treating wastewater uses a lot of electricity.
The biggest energy hog in most ETPs is the aeration basin for biological treatment. You have these massive blowers pumping air into the water to keep the bacteria alive that eat the pollution. Historically, those blowers often just ran flat out 247.
Which is hugely wasteful if the oxygen demand isn't always high.
Exactly. So the smart fix is to install dissolved oxygen DO sensors in the aeration tanks. These sensors continuously measure the oxygen level the bacteria actually need. That DO reading that controls the speed of the blowers via variable frequency drives, or VFDs. The blowers ramp up only when oxygen is low and ramp down when it's sufficient. Instead of running at 100% all the time, they modulate.
And the energy savings.
Massive. Typically cuts the electricity bill for aeration by 10% to 25%. That's often the single biggest energy-saving opportunity in the entire plan.
Wow. Okay, finally, there's just basic reliability and safety, especially relevant in Bangladesh with the monsoon season.
Definitely. Operational reliability is key. Take the large equalization tanks that buffer incoming wastewater flow. Installing non-contact radar-level sensors with automated pump control prevents disastrous overflows during heavy rains. An overflow can flood parts of the plant, shut down production, and cause major environmental violations. Inside the plant, too, reliable monitoring protects equipment. For instance, reverse osmosis RO systems used for water recycling have membranes that are very sensitive to pH fluctuations. Good pH monitoring and control upstream extends the life of those expensive RO membranes significantly.
And the Civar Textile ETP upgrade example really tied all these benefits together.
It did. That facility implemented the trifecta: DO control for aeration, conductivity-based automation for chemical dosing, and radar-level control for the equalization tanks. The results were clear and immediate. Their electricity consumption dropped by 14%, their chemical costs went down 17%, and critically, during the last monsoon season, they had zero overflow incidents, ensuring they stayed compliant and operational while some competitors might have struggled.
It perfectly illustrates that final synthesis. Clean water isn't just compliance, it's efficiency, savings, and reputation. Reliable measurement makes treatment predictable. Quote. Well, that brings us almost to the end of this really extensive journey across 8 absolutely vital sectors of the Bangladesh economy. We've gone from the searing heat of a steel furnace needing 1600-degree control all the way to the microscopic purity needed for a pharmaceutical tablet. Quite the range.
It really is. And what's striking, looking back across all of them, is that common thread, that common language they all speak: precision measurement. Didn't matter if the challenge was nailing that 0.7% billing accuracy for natural gas in the power sector, holding a 5-degree temperature window for perfect color in textiles, or choosing a PTFE lining so a flow meter could survive concentrated acid. Reliable, accurate data was the absolute baseline requirement everywhere.
And it's crucial to remember what the customer, the plant manager, the engineer is really buying here. When they issue that purchase order, maybe for millions of taka, they're not just buying, a shiny metal object with wires coming out of it. They're buying something much more fundamental.
That's the core insight, isn't it? It ties everything together. They aren't buying sensors, they are buying outcomes. They are buying control, they're buying confidence, they're buying continuity. If their biggest headache is inconsistent product quality, they're buying consistency. If they're getting hammered by environmental fines, they're buying compliance, buying peace of mind. If their instruments keep failing after 6 months because of corrosion, they're buying endurance, reliability. The instrumentation is the crucial link, the translator that turns these complex engineering needs into tangible, measurable value that shows up on the bottom line.
Let's bring it all together then with that grand slogan that really captures the essence of everything we've discussed today.
From color to concrete, from taste to turbine precision is the language of every industry. When instruments measure right, industries thrive.
Couldn't have said it better. Thank you, listener, for sticking with us on this deep dive, and thank you for providing the incredibly rich source material that allowed us to explore how this world of instrumentation truly keeps Bangladesh's industries running, growing, and increasingly compliant.
Yeah, it's been fascinating. And maybe just to leave you with one final thought to chew on. We've seen today how compliance mandates and the relentless drive for efficiency are pushing huge investments in this technology. So, thinking ahead maybe 5 years down the line, which specific technological shift that we touched on will likely prove to be the single biggest industrial game changer for Bangladesh? Will it be something like the Memosyn's digital concept, bringing that unparalleled traceability and validation ease, especially critical for pharma exports? Or will it be the universal rollout and impact of those mandatory real-time OSIM systems for wastewater, forcing a new level of transparency and efficiency across all major industries? Which one unlocks the most fundamental, verifiable value nationwide? That's maybe a good topic for your own deep dive.